Okay, so in the last lecture we learned how to draw shear and moment diagrams using the method of sections. The method of sections is good because it's very difficult to forget how to do it, since it's essentially just taking section cuts and applying equations of statics. But it is significantly slower than the graphical method. So using the method that I'm going to teach you in today's lecture, you can draw shear and moment diagrams very, very quickly. And that's because there is a mathematical relationship between the distributed load acting on the beam and the shear diagram and the moment diagram. Okay, so I'll show you why that relationship exists. So we're just going to take a beam here, for example, and it's going to just have some distributed load acting on it that sort of varies in some manner. It doesn't matter that it's increasing like that. The line between here could be wild. Right? It's a distributed load that's just some function. And we've got some support reactions, of course. There we go. And what we're going to do is we're just going to look at the free body diagram of a section cut of this beam, a really thin section cut delta L. Now, you never actually do this in practice, of course, because if you take two sections, make a section cut on two sides like that, you're going to end up with unknowns. But in terms of what we're doing here, this is useful. So here's the thin section cut that I've taken. Now, if that delta L is small enough, the distributed load acting on top of this is going to be approximately flat. Now, this distributed load we'll call variable W. So this is W here. This is delta L down here, and the section is, let's look at the right hand side. It's going to have some internal shear, let's say V, and on the right hand side there's going to be shear as well, and we'll just put those on in the positive directions we've defined. Now, if the shear on this side is V, and we also have a downward distributed load, then the shear on the other side has to be a little bit larger than V, so we'll just call it V plus delta V, some small increase in shear. And then similarly, let's put our internal moments on in the positive direction. So if this is M here, then the moment on this side in the same way would be M plus delta M, so a small increase in the internal moment. So there we go. Now what we're going to do is we're going to look at taking first some of the forces in the y direction for this small section cut of beams. So if we do sum of the forces in the y direction equals 0, and this is for the small section cut of beam that we've taken out, we have, what if we do positive being upwards? We've got V plus delta V, and then we've got a minus V, so negative shear acting on the other side, and then we've got the resultant of that distributed load. Now again, if delta L is small, so W is approximately constant over that length, then we can just write W multiplied by delta L here. That equals 0. Okay, so we've got a V and we've got a minus V, so those cancel out. And then a little bit of rearranging here. We've got what? Delta V over delta L equals W. Now let's take the limit of this as delta L goes to 0. And what do we get? We get that dV dL equals W. Okay, so that's an important relationship right there. So in words, what that says is dV dL. We know what dVs, so that's the incremental change in shear with incremental change in length. So that's the slope of the shear diagram. So the slope of the shear diagram equals the value of distributed load. So that's the relationship between distributed load and shear. So at any point along a beam, the value of the distributed load at that point or at that length position L gives you the slope of the shear diagram. Okay, so I'll write that. So slope of shear diagram is value of the distributed load, right? And then we can do a bit of a rearrangement of that equation to get another useful relationship. So if we've got dV equals WdL, and then we integrate both sides of that, we get the change in shear from point 1 to point 2 is the integral between 1 and 2 of WdL. Okay, so that says that the change in shear between any 2 points is the integral of the distributed load between those same 2 points. Okay, so change in shear is area below distributed load. Okay. All right, so there's our relationship between distributed load and the shear diagram. So now to get the relationship between the shear diagram and the moment diagram, what we're going to do is take the sum of the moments about some point A on this little slice of the beam that we've taken out. So I'm just going to grab this here, like so. And we'll paste that onto a new page. There we are. Okay. Now let's do some of the moments. Let's get black. Some of the moments about point A has to be equal to 0 for this little slice of beam if it is indeed in static equilibrium. So what do we have going into that equation? Well, let's pick a direction to be positive. Let's go with, I usually do counterclockwise as positive, so let's be consistent there. Okay, so what do we have here? According to the sign convention that I established, our internal moment on the left-hand side is a negative value, so we've got minus m there. And then our internal shear force on the left-hand side, that passes right through point A, so it doesn't contribute a moment. And then we've got our little bit of distributed load, so the resultant from that is going to be, and that's acting in the negative direction as well. So we've got negative, and then the resultant is W multiplied by delta L. The moment arm away from point A is delta L divided by 2. And then we've got our shear force on the right-hand side, V, and that's located at delta L away from point A, and that's also in the negative direction, according to the convention that I established, so minus V delta L. And then finally we have the internal moment on the right-hand side, and that's in the positive direction. So we've got plus M plus delta M equals 0. Okay, we've got a negative M there and a positive M there, so we can get rid of those. And can we get rid of anything else? No, we can't get rid of anything else. So let's have our delta M over on this side, and we'll move the minus V delta L to the other side, and same for W delta L divided by 2, and then we'll divide through a delta L. So we've got delta M delta L equals V plus W delta L divided by 2 is what we'd have. And then we'll do the same thing. So the limit as delta L goes to 0. And as delta L goes to 0, that plus W delta L term here, that's going to go to 0. So what we're left with is dm dl equals v. So what does that say? That says that the slope of the moment diagram, which is dm dl, is equal to the value of shear. So at any point L along the length of a beam, the slope of the moment diagram is equal to the value of shear, or the value of shear gives you the slope of the moment diagram. So value of shear gives slope of moment diagram. Okay. So value of, from our previous page, we had value of distributed load gives slope of shear, and now we have value of shear gives slope of moment. So you can see how these are related to one another now. Now again, we can do a bit of rearranging here and get another useful expression. So we can have dm equals vdl, and if we integrate both sides of that equation, then we get the change in moment from point 1 to point 2 is the integral between 1 and 2 of vdl. So the change in moment between any 2 points on the moment diagram is equal to the area under the shear diagram between those same 2 points. Okay. Change in moment is area, then shear diagram. Okay, so we can use those rules that we've just established to very quickly and easily draw shear and moment diagrams. Okay, so let's draw the rules for drawing shear and moment diagrams using the graphical method. So let's start with the shear diagram. So rules for our shear diagram. Okay, and then I'm going to divide the page in half here, and then we'll do rules for the moment diagram on the other side. So rules for the moment diagram. So rules for drawing shear diagram, rules for drawing moment diagram. These are easy. There's only 4 rules for drawing a shear diagram using the graphical method. The first rule is that the shear diagram must start and end at 0. Okay. Second rule is that point loads cause vertical jumps on a shear diagram. Okay. Point loads causes vertical jumps on a shear diagram. If the point load is upward, you jump upward. If the point load is downward, you jump downward. And the magnitude of the jump is equal to the magnitude of the point load. Okay. So point loads cause it would be nice to have a C there. Vertical jumps. And then we have upward load, upward jump. Okay, and vice versa. 3. Rule number 3 is at any point along the length of the beam, the value of the distributed load gives you the slope of the shear diagram. Value of the distributed load gives slope of shear diagram. Okay. And the fourth rule is that the change in the value of the distributed load between any 2 points is equal to the area underneath the distributed load. Okay. Change in shear between 2 points is area under the distributed load between those points. Okay, so those are the four rules for drawing the shear diagram. Now, in terms of the rules for drawing the moment diagram, there are also 4. And the first rule for drawing a moment diagram is that the moment diagram must start and end at 0. Okay. Second rule. So if point loads cause vertical jumps on a shear diagram, you can guess what is going to cause a vertical jump on a moment diagram, a point moment. So point moments cause vertical jumps. Okay, and if the moment is clockwise, it's a jump upward. And if the moment is counterclockwise, it's a jump downward. In either case, the size of the jump is equal to the value of the point moment. Okay, so clockwise point moment is jump up. Okay, rule number 3. Rule number 3. So for moment diagrams, at any position along the length of the beam, the slope of the moment diagram is given by the value of the distributed load at that position. So slope of the moment diagram equals value of the shear diagram. Slope of moment diagram is value of shear, or the value of shear gives the slope of the moment diagram. And rule number 4, a change in moment between any 2 points is equal to the area under the shear diagram between those same 2 points. Change in moment between 2 points equals area under shear diagram. Okay. So 4 rules for drawing the shear diagram and 4 rules for drawing the moment diagram. So let's look at a couple of simple examples and apply those rules. So I'm just going to switch to a new page here. So let's look at a really simple beam for starters. Let's get something that looks like this. So let's put a load right in the middle of it. We'll just make this 10 kilonewtons there, and we'll say that we've got a roller over here and a pin over there, and those are going to provide support reactions. If this is right in the middle of those two, let's say distances of maybe 2 meters and 2 meters, then those support reactions are going to be equal. So we've got 5 kilonewtons over here for AY and 5 kilonewtons over here for BY if we change that into a free body diagram. All right, let's stack our shear diagram right below it. We're going to do shear in units of kilonewtons. Set up our axes for that diagram there, and we'll do the moment diagram in kilonewton meters. Again, stack that right below the shear diagram, something like that. And construction lines, one straight down from our 10 kilonewton load, one down from the end of the beam there. A little bit of erasing to get rid of excess. Okay, let's start with the shear diagram. So rule number 1, the shear diagram must start at 0 and end at 0. Perfect. Okay. Rule number 2, point loads cause vertical jumps. So let's move from left to right. So the first thing we get to is a point load of 5 kilonewtons here. That's the support reaction. That's an upward load, so we jump upwards by the value of that point load. So we're going upwards to plus 5. Okay. Now moving to the right, now we're in an area here where there's no point load, so we look at the distributed load, and remember the value of the distributed load gives the slope of the shear diagram. The value of the distributed load is 0. There's no distributed load, so the slope of the shear diagram is 0. A line with a slope of 0 is just a horizontal line. So there we go. So we continue horizontally until we get to the 10 kilonewton point load, and then a downward point load causes a jump downward, and we jump downward by the magnitude of that load. So we jump downward by 10 from where we're at. So that's going to bring us to minus 5. And then again, now we're in this section. So look at the value of the distributed load. The value of the distributed load is 0. So we keep moving horizontally with a slope of 0, right? So the value of the distributed load here, value of the distributed load gives the slope of the shear diagram, okay? And then we hit another point load, 5, and that's upwards, so we have to jump up from where we are by 5. And we arrive back at 0, so that's good. We know we've done everything properly. We started at 0, we've arrived back at 0. Good, that means that we've done things properly. So it's a nice little check for ourselves there. So some shading, and then the shear diagram's done, right? Easy, easy, easy. Okay, let's do the moment diagram. Moment diagram starts at 0, ends at 0. Good. Now, there's no point moments acting along the beam, so we don't have any vertical jumps in the moment diagram. Okay, so you can cover up the free body diagram now of that beam because all that you need to draw the moment diagram is the shear diagram. Okay, so let's think about this. The value of shear gives the slope of the moment diagram. Okay, so the value of shear starting from 0 on the left hand side, the value of shear is plus 5, so the slope of the moment diagram needs to be plus 5. So that's a linear line positive slope. Okay, and there we go. Okay, now where do we get to? The change in moment between any 2 points, so delta m from a value of 0 to 5 is equal to the area below the shear diagram, right, between those 2 points. Okay, so if we want our moment at L equals 5, then what we do is take our moment at L equals 0 and add on the integral between 0 and 5 of VDL. Now, the integral between 0 and 5 of VDL, right, that's just the area within that portion of the shear diagram, and that's just a rectangle. So this is very easy then. We've got 0 here, our starting moment, and we've got 5 times 2 here, which is 10. Okay, so we've got a value of plus 10 there. All right, now we're moving into the next portion of the curve right here. And what we need to look at is just the value of shear, because that gives us the slope of the moment diagram. So the value of shear is -5, so slope of the moment diagram. Value of shear is -5, so slope of the moment diagram is -5. So -5. Linear line with a negative slope. There we go. So do we get back to 0? Well, the change between any 2 points, so 5 and 10, has to be equal to the area within the corresponding portion of the shear diagram, right? So that's -5 times 2 is -10. -10 plus 10, yes, we do get back to 0, right? So everything works out there. So there are shear and moment diagrams using the graphical method, right? Really, really quick, really, really easy. So let's do a second really basic example here. Okay, in this case, let's take a beam that just experiences only a point moment. So let's make this 20 kilonewton meters, and let's put that right in the middle. And we'll have a roller on that end and a pin on that end, and we'll say that this distance from the roller to the point moment is 10 meters, and the distance from the point moment to the pin is also 10 meters. Okay, then we've got BY here and AY here. Okay, so let's draw the shear and moment diagrams for this beam. So first things first, let's get our axes set up. Shear in units of kilonewtons is looking like it would be sensible from the loads given on the free body diagram. Moment in units of kilonewton meters. Okay, here we go. Again, a couple of lines here to help us orient ourselves between the free body diagram and the shear and moment diagrams is nice. All right. So before we start drawing, we need those support reactions. So some of the moments about point A has to be equal to 0 would give us B. So what have we got in the direction that I've taken as positive? We've got BY multiplied by a moment arm of 20, and then we've got minus 20 from that point moment equals 0. So BY equals 1 kilonewton then. And some of the forces in the y direction also has to be equal. This will give us AY. So what have we got? AY plus 1, which is BY, equals 0. Right, so in this case, AY comes out to minus 1 kilonewton. Not a big deal, so that just means our assumed direction of the support reaction was wrong when we drew it, so we just cross off the arrow like this and change this to a positive and change the direction of the arrow to be downward like that. Okay, so now let's draw the shear diagram. So rule number 1, shear diagram has to start at 0 and it has to end at 0. Okay, now first thing we get to is a point load, AY. So we jump down because AY is oriented downward by the value of AY. So that brings us to minus 1. Then look in the next section moving towards the right. There's no distributed load, 0 distributed load, 0 slope on the shear diagram. Value of distributed load gives the slope of the shear diagram. So we continue on horizontally. Then we get to the point moment. So what happens to the shear diagram? Nothing. No rules in drawing of the shear diagram that relate to a point moment. Point moment does not affect the shear diagram, okay? Other than the point moment having influenced the support reactions to start with. Now we're in the next section here. Again, no distributed load, 0 distributed load, 0 slope. So let's keep going horizontally here. Okay, and then we get to BY. BY, an upward point load of 1, so we jump up from where we are by 1, that brings us back to 0. So good. We started at 0, we ended at 0. All right, for the moment diagram, if you ever get into a case where your shear or your moment diagrams don't end at 0, don't try and fudge it and make them end at 0. The first thing you want to do is go back and check your calculations for the support reactions, because that probably is where you made the initial error, and that if your support reactions aren't correct and your beam isn't actually in static equilibrium, then your shear and moment diagrams are not going to end back at 0. So that's the first thing to check in that case. So moment diagram rules: starts at 0, ends at 0. So what do we have now? We've got, we do have a point moment, so that's in the center of the beam, so we're going to have a vertical jump when we get to that, but nothing on the left-hand side to start with. So we just start from 0, and then what we do is we look at the value of shear, and that gives us the slope of the moment diagram. So the value of shear in this section here between 0 and 10 is a constant value of -1. So the slope of the moment diagram has to be a constant -1. So linear line, negative slope. And then the value that we get to here is given by the area in the shear diagram here. So -1 multiplied by 10 gives us -10. Now we have our point moment. That's going to cause a vertical jump, and our jump is going to be equal to the magnitude of the moment. Clockwise point moment, jump upwards. So we're adding 20 to -10, and that's going to bring us up to +10 here, +10. Now, again, we're in the next section here, so we look at the value of shear, and that gives us the slope of the moment. So the value of shear is still a constant -1, so we have a linear line with negative slope, and we know we have to get back to 0, so we can connect those two. Let's check that. Do we get back to 0? The change between the moment at a length of 10 and the moment at a length of 20, that change is 10, and that should be the area within the corresponding portion of the shear diagram, which is 1 times 10, 10. So we get back to 0, so all good. So we can do some shading, and then we're done. Again, very, very fast to draw shear and moment diagrams using the graphical method. Let's do a couple of more examples here. So let's do a cantilevered beam. So got something like this where this is attached to a wall with a fixed connection like that, and we've got one load of 10 kip here, another load of 10 kip on the end. That's also a downward arrow. Arrow is pretty sloppy. 10 kip there. And distances, let's make this, let's just make it 10 feet. And this one, let's make that 10 feet to keep our numbers nice and round. Okay, so let's first let's throw in our support reactions. So we've got AY here, and then our moment M about point A. Of course, we're taking point A to be right in the center there, attached to the wall. Now let's set up our axes. So we're going to have shear measured in kip. Okay, we can draw a straighter line than that. And our moment is going to be measured in kip feet. Great. Now let's bring that load down like that, and that load down like that. Good, good. Okay. Before we start drawing, we need the support reactions. So sum of the forces in the y direction has to be equal to 0. We can see that we're going to have ay minus 10 equals 0, or ay equals 20 kip there. So we've got that. And then sum of the moments, we can do sum of the moments about point A has to be equal to 0. So what do we have? We've got the moments from both 10 kip loads have to be counteracted by the moment at the wall. So we've got MA is equal to 10. That's the first applied load there. It's at a moment arm relative to point A of 10 feet. So we've got 10 multiplied by 10 plus 10. The other one, its moment arm is 20. So we've got 100, 200, 300 kip feet there. Okay. So let's draw our shear diagram to start with. So shear diagram has to start at 0 and has to end at 0 there. First thing we encounter is an upward point load of 20, so we jump upward by 20. No distributed load, so 0 distributed load, 0 slope. Value of distributed load gives the slope of the shear diagram. Then we hit the 10 kip load and jump downward by 10, so that leaves us with 10 remaining. Then we go across horizontally, another 10 downwards, so we jump downwards by 10. That brings us back to 0. Good, good. Okay, now for the moment diagram. Moment diagram starts at 0 and ends at 0. The first thing we have is a point moment, the moment at the wall, MA. That's counterclockwise, which is a jump downwards. So we're going to jump downwards from 0 by the value of the moment. So we're going to minus 300 kip feet there. Okay. Now, we don't have any more point moments, so all we need to do is look at the value of the shear, which gives us the slope of the moment. So in this first section here, right, the value of the shear is a constant value of plus 20. So the slope of the moment diagram has to be a linear line with a positive slope of 20. So we're going linear line, positive slope. There we go. And where do we get to? Well, the change in moment between any 2 points has to be equal to the area below the shear diagram between those 2 points. So we take minus 300 and add on the area of the corresponding portion of the shear diagram. So that gives us minus 300, right, plus 20 times 10 is minus 100. Okay. Now we're in the next segment. So value of shear gives the slope of moment. Now the value is 10, so we have a linear line with a positive slope, but it's not as steep a positive slope. So something like that. We know we need to get back to 0. Let's check if that's true, because the change, which is 100, should be equal to the area between the corresponding portion of the shear diagram, which is 10 multiplied by 10, which is 100. So that checks out. So we do, in fact, get back to 0, which is good. Okay, so we did everything correctly. Now let's look at maybe let's do the example that we did in the previous class, or in the previous lecture. So we had, let's do both of those examples. So for the first one, we had a beam that was like this. It had a 15 kilonewton load in the middle. It had a 5 kilonewton per meter load like that, and we had a point moment here of 80 kilonewton meters, And then I'm just going to put on our support reactions. We don't want to bother calculating those again. Our support reactions were what? 5.75 over here at A and 34.25 kilonewtons over here at B. So let's set up our axes. V kilonewtons. And we're dropping that down like that. And then we're going across. We go. And our moment diagram in kilonewton meters. Okay. Then again, bring down some helpful lines for constructing these diagrams like that. Okay, so let's do this. Shear diagram starts at 0 and ends at 0. All right, first thing we have is a point moment. Point moments do not affect shear diagrams. The next thing we have is a 5.75 kilonewton point load upwards, so we jump upwards by plus 5.75. There we go. Now we're into this section of the beam. The distributed load is 0, so the value of the distributed load gives us the slope of the shear diagram. So we have 0 slope. Now we've got a 15 kilonewton load downwards, so we jump downwards by 15. Right, so 5.75 subtract 15 minus 9.25 there. And then we've got a distributed load, and its value is 5, but the load is pointed downwards, so the value is -5. So our slope of the shear diagram has to be -5, and that's slope persists all the way until the other side of the beam, or all the way to the other side of the beam. Support reaction at B, so we've got a linear line with a negative slope all the way from where we currently are to the other supports. So something that looks like this. Okay. Now again, the value that we end up with, we actually know it has to be minus 34.25 because we have a point load 34.25 upward and we need to get back to 0, so this must be minus 34.25. Now let's just check. We can double check that this is right. Know that the change in shear between any 2 points, so between this point and this point, that change in shear has to be equal to the area below the corresponding portion of the distributed load. So that change has to be that area there. So in other words, the value of shear at L equals, this whole beam was, what, 10 meters long. So we had 5 meters here and 5 meters here. So the value of shear at L equals 10 would be equal to the value of shear that we started with at L equals 5 minus 9.25 plus the area under the distributed load, which is 5 kilonewtons per meter multiplied by 5 meters, right? And don't forget that that distributed load is downwards, so this needs to be a -5 there, okay? There we go. Now the math is looking better on that. So minus 34.25. So the math checks out. All right, some shading here, or some hatching. Perfect. Shear diagram done. Moment diagram starts at 0 and ends at 0. First thing we have is a point moment. It's 80 kilonewton meters. It's clockwise, so that's a jump upwards. So we jump upwards by 80. Okay. Now there's no other point moments, so all that we need to do to draw the moment diagram is look at the shear diagram. From 0 to 5 meters, we've got a shear value that's a constant value of positive 5.75. Value of shear gives the slope of the moment diagram, so we've got a linear line with a positive slope. There we go. Where do we get to? The change in the moment diagram between any 2 points, the change from 80 to there, has to be the area in the corresponding portion of the shear diagram. So we've got m at L equals 5 is equal to 80 plus the area in the shear diagram, which is 5.75 multiplied by 5 gives us 108.75. Okay, so that's that value there, positive 108.75. Now we switch to this side here. So now the value of shear turns negative, so the slope of the moment diagram turns negative, and the slope values become increasingly, or the shear values become increasingly large negative numbers, so the slope of the moment diagram has to become increasingly negative. So a line with a negative slope, and that negative slope gets steeper and steeper. So we've got something like that, a curve downwards back to 0. And again, you could double check that we got back to the right place by ensuring that this area in here equals 108.75. Okay, so a lot faster than when we drew those shear and moment diagrams using the method of sections, right? Okay, last one here, we'll do the other beam that we did for the method of sections, the one with the linearly increasing distributed load. So we had a beam that looked like this, was a total length of 18 feet there, and we had a 2 kip per foot load on that side, and that increased in a linear fashion to a value of 6 kip per foot on the other side of the beam, like that. Our support reactions were 30 kip on that side and 42 kip on that side. So let's set ourselves up for our shear and moment diagrams here. So we've got shear diagram with units of kip here, and our moment diagram with kip feet. Okay, brilliant. And let's do our moment diagram, or our shear diagram first, sorry. So our shear diagram, starting rule, actually let's draw these lines so we know where we're going to first. Okay, great, now we're set up. So shear diagram, rule number 1, starts at 0, ends at 0. First thing we get to is the point load of 30 upwards, so we're jumping up by 30. Then we look at the magnitude, or the value of the distributed load to give us the slope of the shear diagram. That's 2 kip per foot, but it's downwards, so it's -2. So we know that we need to be starting off with a line that has a negative slope here. Now, that value of distributed load increases moving along the beam. So we have increasingly negative values of distributed load, so we have to have increasingly negative slopes on the shear diagram. So this slope has to remain negative, and it has to become steeper and steeper, so that's a curving line downward like that. And we know where we get to here, because this must be minus 42, so that we can jump upward by 42. Okay, good, good. Let's do the moment diagram now. So we've got a moment diagram that starts and ends at 0. Now, whenever you have a shear diagram that crosses 0, mark that point out and carry it down like this. Right? We don't have any point moments along that beam, so all that we need to do to draw the moment diagram is look at the shear diagram. So starting from a moment of 0, look at the shear, and we've got a positive value of shear. That means the moment diagram starts out to having a positive slope. Okay, so it's heading upwards and to the right. But the value of shear is becoming increasingly small, so the slope of the moment diagram has to become increasingly small until we get to a slope of 0 when the value of shear is 0. And then what happens? Then the value of shear turns negative, so the slope of the moment diagram turns negative. Okay, and the value of shear becomes larger and larger negative values, so the slope of the moment diagram has to become larger and larger negative values. So we've got to curve back down to 0, like that. So the graphical method has given us the shape of the moment diagram very, very quickly. But we still need to find out what the value here is for our maximum moment, right? Now, the value for that maximum moment, the change from the start to that maximum point there is the value of the maximum moment, and that is given by the area within the corresponding portion of the shear diagram, right? So this area here is equal to our maximum moment M max, where this is M max down here. Now, this is a curvy line we've got there, so the only way to figure out that area is to get an equation for the line and integrate it between 0 and wherever it crosses the axis. Now, that's not a problem because we know that we can easily get that equation for shear by using our relationship. So we had dV dl is equal to W, right? Which we can rearrange to say that the equation for shear is going to be the integral of W dl. So if we had an equation for our distributed load, which is easy to get because we know that the distributed load is just a linear line, then we could integrate that and we'd have our equation for shear. Then we just set that equal to 0, solve, figure out where it crosses the x-axis here, and then integrate between 0 and that point. Easy. Now, when you're figuring out what the equation for distributed load is that you're going to integrate, I'd recommend you actually draw a quick sketch of how distributed load varies with length. And that's because if you just look at your free body diagram, you're going to be tempted to write the equation for your distributed load with a positive slope, where in reality, if you graph a quick sketch of the value of W versus the value of L, you can see that W starts off as -2 because that's a downward load, and it goes to a value of -6 over a length of 18 feet. Okay, so if you've got that linear line, then it becomes very easy to write the equation for W. So you have W, and then our slope here, the change in y over change in x. So the change in y is -4, and the change in x is 18, L plus the y-intercept, which is -2. So there we go, -2/9 L -2 is our equation for W. So we can integrate that. V is the integral of W dl, which gives us -2 over 18 L squared minus 2L plus C, our constant of integration. Okay. Now, for that constant of integration, all we do is take the value of shear at 0 and plug it into that equation. So we know what the value of shear at L equals 0 is. It's plus 30. So this is 30. And that equals C because that's the only term we have left in that expression. Okay, so now we've got V is minus, here we go, 1/9 L squared minus 2L plus 30. And we can set V equal to 0 now and solve for what L is. So if we go V equals 0 minus 1/9 L squared minus 2L plus 30, and then solve for L. Two roots out of that, one of them lying within the length of the beam, 0 to 18 feet, the other one lying outside of that. So you want to take the root that makes physical sense to the problem. So that comes out to be 9.73 feet. Right, so now flipping back, we know that this position is 9.73 feet right there. So now, in order to get the maximum moment, we just need to integrate the equation for our shear curve between 0 and 9.73. So here we go. M max is going to be the integral between 0 and 9.73 of VdL, integral between 0 and 9.73 of minus 1/9 L squared minus 2L plus 30. And if we do that integration, we get a value of minus 163.1 kip feet. Okay. So, again, the graphical method, very, very quick. We were able to draw the general shape of the moment diagram and the shear diagram very fast. The graphical method doesn't completely save you from doing any math, but the math on this is very quick to figure out what the maximum moment is. Just writing the equation for the distributed load, linear line, easy equation to write, integrate that to get the quadratic curve for the shear, or the equation of the shear curve, and then set it equal to 0, figure out where it crosses the x-axis, then integrate between those 2 points to get the maximum moment. All right, so you should be well set up now to try and draw some shear and moment diagrams on your own using the graphical method. And from this point on in the course, I'll never, when you have to draw a shear and moment diagram, I'll never make you draw a shear and moment diagram using the method of sections. You'll always be able to use whichever method you want, and you want to use the graphical method because it saves so much time. So learn that one and practice and get comfortable with it. After you get the hang of the fact that the values in the plot above give you the slope in the plot that you're working on, then it becomes very quick to draw them. Okay, I'll see you next time for lecture number 9.